Welcome. It has just gone 7 p.m, Wednesday, the 11th of May, and you are watching episode 48 of Regional Wrap. Regional Wrap, providing insight on the issues affecting regional Australia and giving a voice to regional residents. My name is Bill Bates, and joining me on this episode, Climate Change, a 5-decade journey, is my guest, Professor David Karoly. Professor Karoly is an honorary professor in the School of Geography, Earth and Atmospheric Science at the University of Melbourne, and is an honorary senior research fellow of the Melbourne Climate Futures. He is internationally recognised expert on climate change and climate variability. Studying applied mathematics at Monash University, he later became interested in meteorology, and in 1980 received a doctorate of meteorology from the Reading University in England. Returning to Australia in 1995, Professor Karoly became the director of the Cooperative Research Centre for the Southern Hemisphere Meteorological School at Monash University. In 2003, he was appointed Professor of Meteorology in the School of Meteorology at the University of Oklahoma, returning to Australia in 2007 to join the School of Earth Sciences at the University of Melbourne. From 2012 to 2017, Professor Karoly was a member of the Climate Change Authority, which provides advice to the Australian government on responding to climate change, including targets for reducing greenhouse gas emissions. In 2018, he was appointed as the leader of the Earth Systems and Climate Change Hub in the Australian Government's National Environmental Science Program based at the CSIRO. Professor Karoly was involved in the IPCC assessment reports 3, 4, 5 and 6 in several different roles. His work, along with that of many other lead authors and review editors, contributed to the award of the 2007 Nobel Peace Prize, which was won jointly by the IPCC and Al Gore. He was awarded the 2015 Royal Society of Victoria Medal for Scientific Excellence in the Earth Sciences and was elected a Fellow of the Australian Academy of Science in 2019. Welcome, David.
Hi, Bill, and you've used up half the length of the program going through all of that detail in the bio. I should have told you you shouldn't go through that amount of material.
No, that's fine. I do it for all the. And I'd like to thank you for coming on and soldiering on, seeing that you have COVID, and it was given to you from courtesy of roundabout Cairns in North Queensland, and you've taken it back to Melbourne.
Unfortunately, that is an accurate story as opposed to misinformation, but it's clear that some aspects of climate change information focus a little bit more on misinformation than they do on factual accuracy.
Oh, just on the conversation there, how did you enjoy North Queensland anyway? I mean, you obviously did a little bit of touring. You didn't just come to Cairns, you went to Garumba. So how did you get to and from Cairns and around North Queensland?
Look, I love North Queensland. This was a follow-up trip to where we'd come in 2019, 3 years ago with our grandchildren. Went to Green Island. I've been to other islands and visited other parts of the Great Barrier Reef, but we hadn't been inland to Kuranda previously from Cairns, and so we spent a day visiting Kuranda and then time out on Green Island, and it was fantastic. We had a surprisingly good weather period, and didn't have heavy rain except on Sunday.
Well, we're having our share now, although Kansas has just got the end of it. It's Townsville and South that have really been hit hard, and this year southeast Queensland and northern New South Wales have been hit extra hard, where we've actually had a bit of a low rainfall for the year, and we're only just catching up in April and May now, but we're about 600 mils down from the beginning of the year through to March. But obviously people down in southeast Queensland who want all our money and that also wanted all our rain this time, but I think they got more than they bargained for.
Yep. And as you know, it's a large variability of rainfall in the wet seasons from year to year. And this one is typical of what we know is a influence from La Nina, or the colder ocean temperatures in the Central Pacific, and the warmer ocean temperatures in the northern part, in the regions around the north of Australia, which lead to, above average wet seasons. And that's exactly what we've seen, particularly along Eastern Australia.
Just one thing missing from your bio. You graduated from Reading University, which is part of Oxford, isn't it? Part of Oxford University?
No, University of Reading is completely independent from Oxford, but I was very lucky. I had an opportunity to go there and be one of the first 2 graduate students of Professor Brian Hoskins, and he took me on as a graduate student. He's since been knighted for his services to atmospheric science.
You graduated in 1980 and you came back to Australia in 1995. What, did you get a combi van for 15 years and drive around Europe, or?
No, that was the part of the intro that wasn't quite correct. That was just the gap in some of the bio information. I actually returned to Australia in 1980. Christmas Day, 1980, returned to Australia then. I'd promised my parents that I'd finish my PhD and be back for Christmas. Returned then, and then had a postdoctoral position in CSIRO, and then worked at Monash University from 1983 onwards. So I've been true blue, Dickie Die Aussie throughout my career, except I keep traveling to positions either in the UK or the United States.
Okay, we'll move on to the general conversation about climate change and some of the science. I suppose the real emphasis is, although there's basically 4 major greenhouse gases, we've got carbon dioxide, methane, and nitrous oxide. And of course, there's fluorocarbons and all those things, but they're way down in the scale. And the other one is, of course, water vapor. But looking at the Workgroup 3's summary for policymakers, there's a little diagram there in regards to the amount of emissions and the projections from about 1990 to 2020. I might just share that at the moment, and we can go on to discussion about greenhouse gases. That I'll share it. Yep, that's better. Now we can see it. That's from Working Group 3, and it's basically got the in gigatons, which is somewhat a little bit difficult for most people to get their head around, a gigaton of carbon dioxide or whatever. But that's an overall figure of all greenhouse gases, and 75% of that is carbon dioxide, which equates roughly to 45 megatons for 2020 or 2019 there. And it's obviously gone up from about 40 to nearly, the total is nearly gone up from 40 gigatons to 60 gigatons over that's 30 years. And it's got to continue to rise. And that's the thing that basically we've got to address as we move forward. Now, with your research in that, what's your sort of consensus in regards to how we're going to deal with this, and how much the impact is against sort of natural variability versus now the anthropogenic contribution?
Yeah, look, that's a really important question, Bill. And, it is clear that, first of all, carbon dioxide is the most important long-lived greenhouse gas in the atmosphere. And the increases that we've seen from, say, 1750, when the concentrations were about 280 parts per million in the atmosphere, to carbon dioxide concentrations now are about 410 parts per million. It's grown by more than 40%, close to 45%. And that increase is pretty well completely due to human activity from burning fossil fuels and carbon dioxide. And I've got a graphic I'd like to show you, Bill, which sort of demonstrates why we know that the increase in carbon dioxide is due to human activity. So I'll share that with you now. Oh, there we go. Something's gone wrong.
That's the green button bottom of the screen.
Yeah, no, it's just that I had didn't have my PowerPoint up. I'd hidden it, and I just have to get, yeah. That's better. Sorry about that.
Yeah, here it comes.
Okay, so I'm going to focus on this graphic in the top left-hand side of the screen. And what it shows is over the last 1,000 years, or in fact, 1,020 years roughly, the carbon dioxide concentrations in these dots from carbon dioxide extracted from ice cores in Antarctica. And there's little bubbles of air trapped in the ice. You can extract the carbon dioxide from different slices of the ice going older. We can, in fact, get carbon dioxide concentrations back for 800,000 years, but I'm only showing that last 1,000 years. And then the observational data from direct observations from Cape Grim in Western Tasmania is just these little spots right up the top. And what we see in these is that the carbon dioxide concentration, as I said, was 280 parts per million, and now it's over 400 parts per million. Now it shows the increase, and it's way above the natural variability over the previous 1,000 years. But that's not the most important part. The more important part is this graphic, which is almost the mirror image. It shows essentially another set of dots, which is running pretty stably up here, and then it plummets down as the carbon dioxide increases. And that is the ratio of the carbon dioxide with a carbon isotope, carbon-13, the ratio of the carbon-13 carbon dioxide to the carbon-12. Now we can look in the bottom left-hand side, and that shows why carbon-13 is reduced during photosynthesis, or when the carbon is taken up in the ocean. And photosynthesis preferentially takes up carbon-12, carbon dioxide. Fossil fuels are photosynthetically processed vegetation or phytoplankton, and therefore they're plant material. And the same with land clearing. When we burn fossil fuels, it releases carbon-12 enhanced carbon dioxide, so the ratio of the carbon-13 falls. And that graphic here with the plummeting of carbon-13 carbon dioxide that mirrors the growth in carbon dioxide overall demonstrates that the decrease in the carbon-13 isotope that accompanies the CO2 trend is exactly what we would expect, and shows that the sources of the increase in carbon dioxide are burning fossil fuels and land clearing due to human activity. There is no doubt. Some people say other things, but there is no doubt that the increase in carbon dioxide is due to human activity. And another critically important aspect is that if we want to wait for natural processes to suck out the carbon dioxide in the atmosphere, like growing more trees or the carbon dioxide to be taken up in the oceans, don't hold your breath. We know that it will take between 1,000 and 10,000 years for the carbon dioxide we've added to the atmosphere over the last 100 years to be removed by natural processes alone. We also know that Mr. Dyson, with his vacuum cleaners, has not yet invented a carbon dioxide vacuum cleaner to suck carbon dioxide out of the atmosphere. So we're going to have a long-term problem if we continue to increase carbon dioxide in the atmosphere.
I suppose the other thing is that that 280 during the most of this interglacial period it bounced along a little bit, but not much. And right up until I think about 1900, it was only after 1900, I think, that we actually broke 300 parts per million. But then we sort of picked up the rate as industrialisation took off worldwide, and there was a global economy rather than the original industrial revolution. 1750 through to 1800 was pretty well limited to Europe and the United States, and then later in Australia. But as we advanced into the 20th century, of course, we got China, Japan, and all those countries coming on board with industrialization. So now you have a global economy and you have a global input. So it's now a global problem. It's no one nation's problem anymore.
You're absolutely right, and there are a global set of countries that are, contributing to this problem, and the impacts are spread over many, many different countries around the world.
In regards to, even if we go back to 2,280 parts per million, it's still not going to actually give us some sort of utopian climate, is it? I mean, climate's always going to be variable, regardless if we keep it at 280 parts per million, or 300 parts per million, or 400 parts per million. It does fluctuate. So, causes natural cycles. But what the climate science is saying, everything's exaggerated because of the additional CO2.
Yes, that's right. Yeah, and we know that there's year-to-year variability in the global temperatures and local variability. For instance, this year's a very wet season in southern Queensland and New South Wales. So there's large variability, but we also know that what we're seeing at present is being accentuated by the climate change that we've experienced over the last 50 and over the last 100 years.
The other point I'll sort of look at too is all the information out there that climate change is happening, like from our reef bleaching into fires, extreme fires, and other extreme weather events. There's still effects and consequences, and there's zillions of papers out there of this frogs have been affected by climate change. Well, when you talk about the real nitty gritty of climate change, there's really only a few things in the nutshell. And I think it was, if you go back to the 70s, it was probably your observations, the actual measurements of temperature that people noticed, because you and I have been around long enough. When I was a kid, in the 60s, there was quite a few. In Perth, there was a couple of good years of real heat waves. But then in the early 70s, we got the newspaper things where people were saying there was going to be the ice age cometh and things like that. So they were still in a state of flux then. But then obviously the measurements after 1970 odd, obviously started to trigger people into thinking, well, this is going up and it's continuing to go up. So I suppose that's the observation that starts the assessment. Well, temperature's going up. Then of course the next thing is, well, why? And that's basically where James Hansen and others came into the conversation, and they linked the rising CO2 with the additional temperature. So the real factor is that we're really looking at is CO2, temperature, and then the amount of temperature is going to rise because of that CO2. The fact that there's going to be effects from that, they don't really need to come into the conversation in regards to determining what we've got to do in far as resolving the probable increase in temperature. It's about mitigation of CO2.
You're absolutely right that, if we want to limit climate change, then we have to reduce greenhouse gas emissions, and we need to do that rapidly. But if we want to minimize the impacts of the climate change, whether it's on ecosystems or whether it's on coral bleaching on the Great Barrier Reef, or the impacts in terms of increases in bushfires and frequency and intensity, then we have to know how the different systems are being affected. So it's not just understanding the temperature changes, it's understanding the impacts on weather events, well, weather and climate events, and then the impacts of those on ecosystems and on people in terms of human health and sea level rise and things like that.
If we can just go on the conversation in regards to greenhouse gases, I mean, I think it goes back into about 1850s or 1840s when I think John Tyndall or something was credited for giving some definitive results in regards to the impacts of the different greenhouse gases. Although I did pick up a bit of a note there that a lady named Elise Foote, she was the first one a few years earlier, but hers wasn't quantifiable, whereas Tyndall sort of started getting into the nitty-gritty of a more controlled experiment. So the knowledge that greenhouse gases have been around and their effects have been, it's from the 1850s. Would that be correct?
That's absolutely correct. But at that stage, no scientists or no one had really looked at what this might mean in terms of the impact on the climate, just that there was observed increases in greenhouse gases. It was a scientist, Svante Arrhenius, who had essentially done a very simple, what might be described as back of the envelope global radiation balance analysis that looked at how the increase in carbon dioxide would have an impact on the global temperature, looking at the global radiation balance. And he estimated that the temperature rise would be of the order of 3 degrees for a doubling of carbon dioxide concentrations. And that is still roughly the sort of current estimate for the sensitivity of the climate system to a doubling of carbon dioxide. The only thing that he got wrong was how quickly humans might be able to dig up coal and burn it quickly enough. He said it would take more than 300 years to double the carbon dioxide concentrations in the atmosphere from essentially 280 parts per million to 560. And at the rate we're going, we will hit the doubling, if we were to have unmitigated burning of fossil fuels, we would easily hit that well before 2100.
Well, the doubling is 560 parts per million. And the way China and India are going, it's got to get there anyway. It doesn't. I can't see them doing enough to stop it, and they're the biggest contributors. So I think we're in for that. But the other thing that's very interesting in regards to greenhouse gases is they're essential to life on the planet. If we didn't have greenhouse gases, that's water vapor, carbon dioxide, methane to a lesser extent, and then nitrous oxide. The global temperature would be about 33 degrees Celsius lower than what it is. So we don't want to sort of pull the blanket out of under greenhouse gases because we need it, but somehow we've got to find that happy medium.
You're absolutely right. And we know that the carbon dioxide concentrations have changed dramatically and were much lower in the ice age periods than we currently have or had over the relatively stable period. You talked about this sort of stable climate period from 1,000 years ago, 280 parts per million, and pretty stable at that for essentially most of the last 1,000 years. And that was a pretty stable climate period that, most of, the development of the society has taken place in a relatively stable climate period. But you're right that what we need to think about is what would be the impacts of the long-term increases in carbon dioxide. And look, India and China have both made commitments to reduce their emissions and significantly, reduce them. So I know you have some doubts about whether that will take place.
You've got more faith in them than I have.
Yeah, look, it's not clear that the Australian government has any commitment to its fair share of emission reductions as a developed country, but that's a political perspective, and I know we were going to try and concentrate on the science here.
Yeah. Oh, it's just interesting in regards to I wouldn't pin any faith in the Chinese government whatsoever. And the other thing is, if they approve the equivalent of Australia's whole energy output through on coal-fired power stations each year, well, that's a bit of a worry. So I wouldn't give them any gold star at the moment.
No, you're absolutely right.
Just in regards to other greenhouse gases, and methane's probably the major one, the second major one. It doesn't seem to be, looking at the graph I showed before, it's been around to 20% of the greenhouse gases from 1990. It's actually dropped off to about 18% of the total. But so it's sort of an indication that there's a fair bit of natural methane is in the mix rather than just human activity as well.
That's correct. And look, there are natural sources of methane from swamplands. Methane is produced by the anaerobic decomposition of vegetation underwater. So, swamplands produce bubbling up methane, and there are other sort of sources of methane. It's not, exclusively from agriculture, but other activities as well. So we know that there are natural sources of methane, but we also know that actually the change that we've seen in methane over the last, and it's been very substantial. I mentioned that there was 45% increase in carbon dioxide concentrations. The concentrations of methane have nearly doubled since the pre-industrial period, and that has a major impact in terms of warming the climate system, because a ton of methane is dramatically more powerful as a greenhouse gas than a ton of carbon dioxide emitted into the atmosphere, because it absorbs infrared radiation in different wavelength bands than carbon dioxide does or that water vapor does. So it's a very efficient greenhouse gas compared to carbon dioxide.
I think both the warming potential of water vapor and carbon dioxide is one, and for a 20-year and 100-year period. Methane's 20 times higher for a 100-year period, but 80 times higher for, I think, 20 years period. And of course, then nitrous oxide, fortunately, there's not too much of that. That's about 350 times more warming potential. But again, that's down in parts per billion rather than parts per million. You picked the Cape Grim sampling there, and I think the most common or well-known sampling point is in Hawaii at Manuloa, I think. Cape Grim's in Tasmania. Is that because your association with Australian sort of access to data, using that rather than sort of the Hawaiian sampling system?
Well, no, it's not quite that. But really the more lower location is in the Northern Hemisphere and affected by Northern Hemisphere sources of carbon dioxide, whereas the Cape Grim is located in the Southern Hemisphere, and it's more relevant for looking at global carbon dioxide concentrations in the Southern Hemisphere. When we're looking at Antarctic ice cores, it's better to use a comparison to long-term data sets from the Southern Hemisphere. So that's why I used Cape Grim, because there is in fact a small contrast or gradient in the carbon dioxide between the Northern Hemisphere and the Southern Hemisphere, primarily because there's more sources, more emissions in the Northern Hemisphere. We talked about different countries with large emissions, China, the United States, Europe. There are bigger emissions in the Northern Hemisphere. It takes time for that air to move into the Southern Hemisphere. It takes about 6 to 12 months for it to be mixed. So that means there's a 2 to 3 parts per million difference in the carbon dioxide at Cape Grim versus Mauna Loa.
There's also a big difference between the Northern Hemisphere and the Southern Hemisphere in regards to land mass too. I mean, they talk about land mass of the world is basically 30% land mass, 70% ocean. But when you get into the Southern Hemisphere, you're talking about 10% land mass and 90% ocean. So is that some of the reason, like the Northern Hemisphere feels the pain a bit more than we do, quicker?
Well, look, that's a really interesting question. I mean, first of all, Australia, excuse me, Australia has been identified as one of the, if you like, developed countries that has experienced the climate extremes due to climate change, like heat waves, like drought, like bushfires, and like extreme weather events like the extreme rainfall, as you mentioned, in southern Queensland and New South Wales. Australia has been receiving, unfortunately, many of these climate extremes, heat waves, bushfires, extreme rainfall, more so than some other countries. I mean, the United States has been getting those climate extremes that have been linked to climate change as well, and so has Europe, but Australia's been getting them more often than other European countries or North America.
I suppose the other thing in regards to Australia, I mean, the word that I get a little bit terse with is the word unprecedented. And in a lot of cases, the first reaction to a weather event is it's unprecedented. And we had that in the January floods, February floods in southeast Queensland. And and I think that's the first term I've ever heard of a rain bomb used in regards to that flooding event. But really what it was a tropical cyclone that went down to a depression, and it was very slow moving. So, and it just stayed over one place for, you know, an undue period, and it did release a lot of rain. And Miss Palaszczuk got up there within a day or so and said, this is an unprecedented event. And it's a fairly dangerous sort of word to use, because there's a lot of people out there who access records on the internet. And I think it was only a matter of about 2 hours when there was a pile on in regards to the 1891 cyclone that came through Brisbane. The heaviest 24-hour rainfall was actually recorded in the hinterland behind what is now the Gold Coast, in a place called Crowhamhurst, and that was 900 and something millimeters over a 24-hour period. Now, I don't think it's helpful when politicians in particular get out there and say this is unprecedented, and then all of a sudden you get some information. Well, back in 1841 and 1891, this is the information. Do you think some of the language should be toned down a little bit in regards to using unprecedented and things like that? Or do you think you need to have that sort of language to keep the conversation or the focus on the problem?
Look, no, I don't think that we need to use unprecedented for some or many extreme events. But what we do need to know is essentially what the record period or observational period that's used to describe these sorts of data sets. And within Australia, we only have just over 100 years. The Bureau of Meteorology's data sets of essentially high quality rainfall observations and high quality temperature observations really only exist from 1900. And so what it means in terms of, well, in fact, 1910 for the temperatures, 1900 for the rainfall. And there are many locations for which earlier records are not available. What we need to also recognize is that we shouldn't be just looking at, if you like, unprecedented for a single location, but as you described, Bill, looking at the surrounding locations for which related weather events might have essentially affected those regions, and recognize that much the same sort of weather system could have led to higher rainfall nearby, within whatever, 50 kilometers or something like that. I think, though, if there was inland from, I think you said it was the Gold Coast, was that where you were saying the
the hinterland?
Yeah, the hinterland. If it's orographically influenced rainfall, that can often be much heavier rain. The rain in Toowoomba or the rain inland from the Gold Coast region up in the hills, you often get orographic lifting and enhanced rainfall there. And so you've got to be careful in terms of looking at the sorts of rainfall events. But you're absolutely right, using the words unprecedented when it's based on only 100 years of observations and saying that this is a 1 in 1,000 year event is just plain stupid.
Is a bit of a long bow.
Yes, definitely.
But there again, we've only been able to accurately measure, or reasonably accurately measure temperatures for just over 400 years. I mean, I think the longest running record is Central English temperature, but there again, it's not one continuous location. It just happens to be in Central England. And there's actually been a couple of sites, and you're talking about places like Birmingham, which has changed, over the years. So it gets a little bit messy, but I think that's some of the issues. We haven't had this real data set for any length of time. And really, as a civilized nation, as humans, we're only we haven't even blinked our eye in geology terms. At best, we only created cities about 10,000 years ago. So we haven't got too many runs on the board about knowing all about everything.
Yes, Bill, that's quite correct. But of course, when we're trying to look at, if you like, what's likely to happen with ongoing increases of greenhouse gases, or what's contributed to the impacts in the climate from the increases in greenhouse gases, we either need a very effective crystal ball, and I've not yet found a crystal ball that's good for looking into the future, or we need to use complex mathematical models of the climate system for where we can run experiments with what would happen when there were no increases of carbon dioxide in the climate models, or what we get when we've increased the carbon dioxide concentrations, and how well they would simulate the temperatures in Australia or the temperatures around the globe. And I have a graphic on that if you would like me to show it.
Thank you.
Okay, so let me go back to sharing my screen again, and what I just have to do is jump down to the graphic that I wanted to show, which is this one, go up to full screen. So what this shows is from climate models, and not just one climate model, but more than 40 different climate models, simulations that were started in 1850 with these different climate models, and then run throughout the 1850 to 2000 period with the no changes in greenhouse gases. And that's what these grey bands are here. It's the showing the decade to decade temperature variations in the climate model simulations with no increases in greenhouse gases. And it's a pretty stable curve with some variability. And then the thicker black line here shows the observed Australian average temperature from the Bureau of Meteorology, as well as the year-to-year temperature variations. And then underneath that, in this blue band, is the climate model simulations run from 1850, where the data is extracted just over the Australian region and averaged, and then the Australian average temperatures from 1900 right up to 2020. And what you see is that the observations for the decade to decade temperatures agree well with the model simulations run with increasing greenhouse gases. And actually, the models without increases in greenhouse gases can't distinguish or can't be separated from the observed variations until after 1950. And it's only after about 1970 that the observations lie outside the range of just natural variability and no impact or no increase of greenhouse gases. It's after 1950, from the 1960s, 1970s, that you can see a clear signal of the increases in temperatures globally and in Australia from increases in greenhouse gases in the model simulations. And it's only using these models that we can run a sort of parallel set of experiments with and without the greenhouse gases, and we can only explain the observed warming with the human-caused increase in greenhouse gas emissions, carbon dioxide and the other things. Now, it's really interesting because this shows the year-to-year temperature variations as well. 2019 was a record hot year, and it also shows the climate model projections from 2020 right out to 2040, ongoing warming. And this is the range of warming projections from the different models. But 2019, the black summer period, oops, sorry about that. I've shifted and lost the slide. Now we're back again. 2019 turns out to be an average year in the 2040s. It's not an extreme hot year, and that ongoing warming that's due to the greenhouse gases we've had already and the increase in greenhouse gases in the future will cause further warming, and years like 2019 and the black summer period will be typical of a dry year in the 2040s. So unfortunately, we also know that bushfires will be extreme and become more common in the 2040s. Let me stop sharing.
I had Brendan Mackey on the week before last, and we talked about the fire situation. I also highlighted that there's been a shift in forest management over the last couple of decades. We've basically driven out logging out of the forest. We've almost, set aside so much forest that there's almost no human intervention anymore. I sort of suggested, well, don't you think it's pretty important if we're going to have these situations that we actually manage our forests a lot better? We actually log it and do prescribed burning. But his sort of feedback was it's pointless because it's going to get hotter and drier, and it doesn't matter if you have prescribed burning, it's going to burn. So that doesn't make me hopeful or cheer me up. What that makes me say, well, let's get stuck in now and just cut all the forest down, and so it doesn't burn, and just manage it a little bit better or something. But if that's the doomsday scenario, that's pretty frightening. It's that we can't manage, because I think humans are fairly skillful at adapting and intervening to mitigate things.
Look, for sort of typical years in the past, we have been able to manage moderate-sized fires but the sorts of situation we had in 2019, 2020 summer, the Black Summer period, was extreme fire danger periods across much of southern Queensland, New South Wales, eastern Victoria, and led to, you know, major impacts throughout those different regions. And those sorts of conditions will become more frequent. And no amount of logging or fuel reduction burning will stop those sorts of extreme fires occurring. So I agree with Brendan that while we can manage some aspects of, if you like, with fuel reduction burning or using Indigenous approaches to managing the forest land and cool burning, cool temperature burns, what we're not going to be able to do is to prevent the increases in fire weather conditions that we've already experienced with only 1 degree of global warming, and we're likely to hit 2 degrees of global warming by 2050.
Well, I don't like being a defeatist. I don't like the idea of things just progressing to it's always going to be a mega fire somewhere along the line, and we're going to fry every bit of wildlife out there. I think we've got to make a better effort than that. But one thing I would like to go back to is some of your early research in regards to is it Southern Pacific Decade Oscillation, or your early studies, and then how any of that relates to the recent weather patterns, or it does or it doesn't. But one thing I noticed over this year in regards to looking at the weather maps and especially the synoptic charts, one of the interesting things that happened this year, a lot of the troughs came across northern Australia, went across the top of the Cape York, and then about 600 kilometres out to sea, and then hooked down. And that was typical for a fair bit of February and things like that. And it was also, I don't know, it's that sort of time that we should be getting very wet in our cyclone season, and we basically missed out. There was cyclones forming in the Pacific, mainly further out to sea. I think Fiji or the Solomons got hit a couple of times. But even I would sort of suggest that our lack of sort of rainfall up here and the pick up it down in the southeast corner from those slow moving systems, was there any influence from the things you studied in your earlier thing contributing to that?
Look, it'd be nice to think that I could explain the month-to-month weather variations from what was quite a, how would I say, theoretical approach. What I looked at in that analysis for my graduate study was how the sorts of typical patterns of, say, ocean temperatures associated with El Nino can influence the extratropical. So El Nino is the much above average sea surface temperatures in the Pacific Ocean that leads to much drier conditions over Australia, and also leads to significant variations in temperature and rainfall patterns over North America and over South America as well. And the opposite of El Nino is La Nina, and that leads to wetter conditions over Australia. Now, it was that teleconnection pattern, the connection between what's happening in the Pacific and what happens over North America or what happens over Australia. I was looking at the theoretical explanation for why those distant links could happen, but it was based around looking at effectively the variations at relatively large scales given long-term ocean temperature variations or long-term changes in the flow over mountains or topography. It wasn't looking at individual weather systems. And I think that what happened in this wet season, as you said, was very dry in January and February over much of the northeastern part, North Queensland, and then has been wetter again in the sort of April period and later. So what that is really just part of, unfortunately, natural variability that if the Bureau does well enough, it can predict a week in advance, but usually can't be predicted, a month or two in advance.
Okay, we'll go back to the carbon dioxide and the greenhouse gases. In regards to, you took a lot of the emphasis, even through all the reports, is computer modelling and the different scenarios. And I suppose a lot of people, well, I've mentioned it in one of the first subjects with work group ones, and the different scenarios in regards to RPCP 1.5, 2.9. So some people incorrectly associate that with degrees of temperature, where it's actually an increase in the watts per square metre expected globally. In other words, if we put so much carbon dioxide into the atmosphere, it will get to, the greenhouse gas or greenhouse effect will increase the, basically the Duna effect by a couple of watts per square metre extra into that. And that's the sort of scenario. In regards, other than climate models, what do you think is some of the best historical, like we mentioned, ice cores? What other sort of empirical type or things that we can get good proxies from gives us a bit of indication of maybe the last time of civilization on Earth in regards to how the temperature was and how it progressed?
Look, that's a really good question, but we do have a number of, if you like, ecological sources of information, not for daily temperatures, but for annual temperature variations or multi-year temperature variations, often going back for hundreds of years in the past. And these include tree ring data from tree rings that are able to provide an indication of the temperature at which the tree was growing, particularly in alpine areas, and you can get good tree ring data back for hundreds of years. You can extract information like that from ice cores as well to get temperature information, as well as carbon dioxide information from ice cores. You can also get temperature information from the chemical structure of stalagmites or stalactites in caves. So there's a range of different sources of information around that can be used for reconstructing historical climate, but not just historical in the last 500 years, but back for 1,000 years or longer. Getting more accurate information is difficult because we only have good instrumental observational data going back for, in Europe, 200 or 300 years or more. But in Australia, we've only got good observational data for 100 years or so.
Well, there was a show on SBS earlier on in the week. It was quite interesting when they did the tree rings, and the period was, I mean, they get it down to 541 AD through to 548, and they had the tree rings there, and it showed a period of cooling, and also that was at a time that the Roman Empire collapsed, and it was sort of the actual Dark Ages, and a lot of civilizations or advances that we had in civilization sort of decayed away, and archaeology is now providing us with a bit of insight in regards to the climate effect on a lot of these civilizations or this was in particular Mediterranean cities, and also in Egypt. So we are getting a much greater wealth of information in regards to that past history and the effect of climate. on various civilizations in the past.
Yes, and much of that information focuses on the impact of natural climate variations and particularly the impact of colder temperatures. We don't have much information on the impact of warmer temperatures, but the interesting thing is there is one Indigenous population or Indigenous society, the Australian Indigenous communities. They are the only Indigenous population that have survived continuously from the last ice age through 5 degrees of global warming and 100 meters of sea level rise. And their stories and songlines provide great information about how their communities survived those massive changes in climate and how they managed country sustainably and sea country and land country sustainably over the last, 10,000 generations, over the last, 20, 30,000 years.
The ice core information shows that we've gone in and out of glacial periods. I mean, interglacial and glacial periods, because we've actually been in an ice age for nearly 2 million years. An ice age is just simply defined as any period, any geological period where there's permanent ice in both the north and south hemisphere. And that situation has been there for over 2 million years. But we have, as you said, we've got ice cores information going back 800,000 years, and it shows the swing from between glacial and interglacial periods. And the interesting thing I find about that is the interglacial periods, we've had the 250 parts per million. The glacial periods, we've had 180 parts per million of CO2. The frightening thing for me is when we got into those glacial periods, at 180 parts per million, we're starting to touch on a point where it's difficult for trees and that to grow. So we don't, like I continue to say, we don't want to sort of push the CO2 down to a level where trees don't grow. But the situation we're going into now is uncharted territory, because all these interglacial periods, it's been about 280, and now we've gone up to 420 roughly now. Is there anything that you think that would stop us going back, continuing with that cycle that's been around for the last at least 800,000 years? Is global warming and carbon dioxide increase likely to prevent us from going into that cycle somewhere in the future?
Look, that's a very interesting question, and it gets asked a lot. Should we continue to increase carbon dioxide in the atmosphere and burn fossil fuels to keep the carbon dioxide level in the atmosphere high to avoid the next ice age? And there are modeling exercises to look at how the Earth's orbit around the sun and the periodicity of the Earth's orbit is what drives the changes in solar variation that led to the initiation of ice ages. So that modeling of the Earth's orbit around the sun is quite accurate, and based on the multiple periodicities of the 110,000 or 120,000 years and 40,000 years and 12,000 years, when you combine all of those together and look at when the next, if you like, ice age might occur, don't hold your breath. It's unlikely to occur for the next 20,000 years.
Yeah, it's the Milankovitch
cycles.
Yeah, Milankovitch. It's his cycles. I think there's 3 different cycles. There's the elliptical orbit of the sun. It changes from actually circular to elliptical. Then we've got the change in axis, and then we've got, on top of that, we've got a wobble. So there's 3 different things interacting, and they're all got different time period cycles. And so when they coincide, there's only at a set time, and when they sort of separate, that's another time. But this period of interglacial we have now is we're now about 17,000 years into that cycle. From the ice core information, we used to have, I think, about 60 to 70,000 years of glacial periods, followed by about 40,000 years of interglacial. But that cycle has actually changed again. I think the last few cycles are more in the cycle of 70 to 80,000 years of glacial, and about 30,000 years. So it's quite strange that the oscillation sort of is speeded up from the initial ice core samples.
Look, that's somewhat correct, but actually throughout most of the last 800,000 years, if we look at both ice core evidence of carbon dioxide variations and ice core evidence of Antarctic temperatures, typically the periodicity for ice ages in interglacial periods is the ice ages are about once every 110 to 120,000 years, that the interglacial periods typically last only about 20,000 years or so. And therefore, the fact that we've had the end of the last ice age about 15 to 20,000 years ago, people were starting to say, well, therefore we should be preparing for the next ice age. And for most of the last 10,000 years, there has been a slight cooling of the climate system. And as our former Prime Minister, Tony Abbott, said, it was clearly warmer in the Roman period because they were wearing togas and therefore it had to be hot. Well, actually, he's not completely wrong. It was a little bit warmer 2,000 years ago, excuse me, in the Roman era, not just in the Mediterranean region, but across the globe, because there has been a long-term cooling trend from 5,000 years ago or 10,000 years ago, right up until the sort of 1880s. And only after the 1880s, 1900s, have we started to see significant warming.
We also had the
Maunder minimum
period.
Yeah.
Maunder minimum.
Yep.
That's a time that I would not like to experience. I don't know about you. Reading some of the chronicles of the things that happened to the people at that time, the famines, pestilence, plague. It certainly wasn't a good time. So hopefully we don't experience that sort of thing anytime soon. But it was definitely something that I think civilization or mankind was happy to leave and move into the industrial era, although we've now invented another set of problems.
Yes, that's correct.
We've only we haven't touched on some of the things that I'd like to talk about, but maybe we can do another show later on, especially in regards to the radiative forcing in regards to the basically equilibrium sort of effect in regards to the globe, how much heat comes in, how much heat goes out, and also the added influence of the CO2 gases in regards to retaining that nice little doona across our atmosphere. If would you be happy to come back when you're better and sort of talk about that sort of part, and then sort of look at the actual modelling the scenarios, especially RCP's probably 2.6, 3, 4.4, and 6. I think 6 is the one that they now mainly focus on as the thing that we've got to really address. I think the scenario for the RPC 8.5 is probably I think most people have sort of discounted that a little bit, and the focus is moving forward on if we don't do something, it's got to be we've got to be looking at 6 watts per square metre additional greenhouse effect.
Bill, I'd be happy to come back again. I won't be available for June really at all, but it might have to be, you know, back in July or something like that. But I can tell you
that's fine.
The science won't change between now and July for those sorts of things, and the radiative forcing won't change that much unless the cloud is blocking out the sun, and that's what's going to...
I think that discussion on the equilibrium, radiative equilibrium, is a very interesting conversation in regards to moving forward, and all the different other impacts that change that, because if you reduce cloud cover by about 1%, that adds about a 1.6 watts per square metre to the heat that's going to strike the earth. And I think, it's like I say, it's an interesting conversation, which most people would understand with diagrams in regards to the cloud cover effect, the reflective radiation, the absorbed radiation, and that at the moment, I think it equates to about 67 watts per square metre for the greenhouse gas contribution in regards to having that hold in the atmosphere. But I'd like to thank you tonight for coming on. I really appreciate it. We've got through an hour with your COVID, and that's much appreciated that you soldiered through that. But look, I really look forward to the opportunity to say, coming back in July, you'll be 100% fighting fit, and maybe we can have some slides just prepared on those sort of things, because I have seen a number of diagrams for that that scenario with the reflective equilibrium, but there's some good ones and there's some pretty ordinary ones. We probably need to sort out something that's readily explainable to the audience.
Sure. Look, happy to do that, Bill, and you know, keep in touch, and we'll see what we can plan out for doing something in July.
Okay, thanks very much. If you can just stay on there, I'll just wind up now. And sure. If you enjoyed tonight's show, please like, share, and subscribe to our Facebook page, and also subscribe to our YouTube channel. Next week, we'll be looking forward to a conversation on the forestry industry, and that's an extension from one we did last year in regards to the inquiry in New South Wales for sustainable logging, and timber. So look, join us again next week, and welcome, and thank you for your attention. Good night.